From the previous researches, it has been shown that nanotechnology is a powerful tool for a host of the solar system in support of efficient, suitable energy conversion, storage, and conservation in terms of tailoring the interaction of light with materials and enabling the processing of low-cost semiconductors into devices such as photovoltaics, making more efficient photocatalysts for converting sunlight into chemical fuels, developing new materials and membrane for the separation needed in many energy applications, converting chemical fuels into electrical energy and vice versa, and improving energy and power density in batteries, improving efficiency in areas from displays and solid-state lighting to thermoelectric and friction. The power of sun can either be captured actively or passively. Passive solar heating, as you may have guessed, is passive. In other words, it takes advantage of the existing heat generated by the sun to heat living spaces. Passive solar heating can be used in your home to cut your wintertime heating bill and improve comfort. But to fully take advantage of solar energy in this way, some planning is required. Because passive solar heating does not involve any mechanical devices, a home designed for passive solar heating will need to be positioned in a way that allows heat from the sun to enter in winter and be rejected in the summer months. This positioning will vary by the local climate conditions. But in the northern hemisphere, a good passive solar design uses south-facing windows to capture the sun's rays. In the winter, when the sun is positioned low in the sky, the southern-facing windows allow the sun's rays to enter through the windows and heat the home. In the summer months, when the sun is positioned high in the sky, a passive solar home will use a large overhang for shade. This prevents the sun's rays from entering the window and keeps the house cool. Beyond being positioned correctly, a passive solar heating design will also depend on thermal mass of the walls, flooring, and the other objects within the home. Thermal mass can be defined as a material's ability to absorb, store, and release heat. When the sun's rays enter the home in winter months, the heat energy is absorbed by the materials inside the building that have a high thermal mass. This would include materials that are dense, such as stone, brick, and concrete or ceramic tile. These materials absorb and hold on to heat during the period of time that the sun shines on them, and then slowly release that heat throughout the nighttime, keeping the home at a more stable and comfortable temperature. If you live in a climate that has regular snowfall each year, you can get a good idea of how thermal mass works by thinking about the first snowfall of the season. What you likely notice is that the snow easily melts on the road surface, but it clings to the grass and the trees. This is because the dense material that makes up the road has higher thermal mass and it has held onto the sun's heat, causing the snow to melt on the contact. The grass and the trees are less dense and have low thermal mass, so the snow does not melt. Active solar heating is a more involved process than passive solar heating. While passive solar heating employs methods to capture heat from the sun, it does nothing to actively enhance the process. In contrast, active solar heating uses mechanical and electrical equipment to enhance the conversion of solar energy to heat and electric power. Active solar system can generate more heat than passive solar system. For active solar heating, we will need a solar collector, which is a device used to absorb solar energy. First generation of solar cell is made of crystalline structure which uses silicon to produce the solar cells that are combined to make solar cells. However, this technology is not absolute, rather it is constantly being developed to improve its capability and efficiency. Monocrystalline, polycrystalline, gallium arsenide, and emitter wrap-through are cells under this umbrella. Compared to the solar cells that are based on crystalline silicon, thin film technology is less expensive since it uses less material. Solar cell that is made for this technology is very thin, which is around 35 to 260 nanometers. Third generation technology is technology based on concepts which are able to surpass the so-called Shockley-Queisser limit of a single junction solar cell. The Shockley-Queisser limit is a kind of thermodynamic approach to estimate the maximum performance of a single junction solar cell. The AM 1.5 spectrum is incident on a solar cell. We don't allow the solar cell to increase in temperature. This means that all the energy in the incoming AM 1.5 spectrum can escape the system of the solar cell by either the current density generated or by the radiative recombination of charge carriers. As a result, the maximum efficiency which can be achieved is around 33% in the bandgap range from 1 electron volt up to 1.8 electron volt as indicated by the black area in the shown graph. Now, we are going to look at a very fundamental limitation of the photovoltaic effects. What physical principles are limiting the extent of photogeneration? First, one problem is that in a single junction, only one bandgap material is used. A large fraction of the energy in the most energetic photon is lost as heat, as illustrated here. The arrows represent photons with different energies. The arrows on the right indicate how much energy is wasted as heat. Secondly, most solar cell concepts are based on radiance incidence. Higher irradiance means more current generation. Thirdly, every photon only excites one electron in the conduction band, creating only one electron hole pair. The energy of the high energetic photon could be utilized better if they would create more than one excited electron in the conduction band. Fourthly, the photons below the bandgap are not used. They do not result in the charge carrier excitation. Finally, charge carriers populate single energy levels. Light absorption excites electrons and holes up into the conduction or down into the valence band. However, the charge carriers relax very fast, the electron to the bottom of the conduction band and the hole to the top of the valence band. The potential difference between the charge carriers right after the excitation is not utilized. In addition, in the band are no states, so the light below the bandgap does not excite any charge carriers. Tackling these fundamental limitations means that we can develop PV concepts with conversion efficiencies that can surpass the Shockley-Queisser limit. Tackling the first problem, both the third and fifth semiconductor PV technology and the thin film solar technology use the concept of multi-junctions. Several solar cell junctions stacked up on each other with response to different parts of the solar spectrum. The second problem that concepts are based on once on irradiance is tackled using concentrated solar cells. The concentrated technology is applied on multi-junctions based on 3 and 5 semiconductor materials. As a result, the highest conversion efficiencies of 44% have been achieved. This exceeds the Shockley-Queisser limit by more than 10%. The fact that every photon can only generate a maximum one collected electron can in theory be tackled by two approaches. The first one is down conversion, which is a spectral conversion approach. The high energetic photons are split into or more low energetic photons before being absorbed in the PV active part. As a result, high energetic photons can result in more than one electron being collected. The second approach to enhance the charge carrier excitation by a single energetic photon is called multiple exciton generation, MEG. Here, nanostructure semiconductor materials might be able to convert the energy of a photon in two or more excited electron hole pairs. The problem of the non-use of the photon below the bandgap can be tackled with a spectral conversion approach as well. Here, the same low energetic photons which are transmitted through the solar cells are converted into one photon with an energy above that of the bandgap of the semiconductor material. If this photon is reflected back in the material, it can be absorbed. The last problem in the list is that of single population of each charge carrier. In theory, this can be tackled by hot carrier solar cells. Here, the charge carriers are collected just after light excitation before they are relaxed back to the axis of electronic bands. This improves the band energy utilization. Another theoretical solution is the concept of intermediate band solar cells. This is the concept in which intentionally an electronic band within the bandgap is engineered to enable photons below the bandgap to help the additional electrons to be excited as well. Note that besides multi-junction and concentrated approach, none of these concepts have resulted in higher efficiency solar cells or even been demonstrated yet. These other concepts are still in a fundamental research phase. Here we will talk about the down conversion, multiple exciton generation, up conversion, hot carrier solar cells, and intermediate band solar cells. Let us start with the spectral conversion, which results in splitting one photon in multiple lower energetic photons. It might tackle the problem that per photon only one electron is excited. A down converter is a magic material that absorbs a high energetic photon and converts this photon in at least two lower energetic photons. If the energy of both photons is still larger than that of the bandgap of the photovoltaic material, both photons can be absorbed and used for exciting charge carriers. As a result, a high energetic photon, like a photon in the blue visible part, can result in two excited electrons in the blue part. In other words, the maximum theoretical EQE of 100% at the wavelength of blue photon can be increased to 200%. If the photon has enough energy to split into three photons with an energy higher than the bandgap, the theoretical EQE of 300% could be obtained. So, spectral down conversions first convert photon into lower energetic photon, and these photons are used in photovoltaic devices. Multiple exciton generation is another approach which can accomplish the excitation of more than one electron hole pair per photon. The difference with the spectral down conversion is that all fundamental energy conversion steps occur in the PV active layer. In a normal semiconductor material, a high energetic photon has some rest energy which is not used to excite the electron. This excess energy is usually lost as heat. In down conversion approach, this rest energy is transferred as a quantized energy package within the material. A second electron can be excited into the conduction band. It means that the energy in one photon results in two excited electrons. The requirement, of course, is that the energy in the initial photon is at least two times that of the band gap energy. In this way, theoretical EQ of 200% can be achieved as well. If you would have a photon with an energy larger than three times the band gap, theoretical EQ of 300% could be achieved. Both for down conversion and multiple exciton generation, nanostructured semiconductors are studied and developed. These structures are based on so-called quantum dots. Quantum dots are small spherical nanoparticles made of semiconductor materials with typical diameters of a few nanometers. These semiconductor particles still behave like a semiconductor material. However, due to quantum mechanical effects, the bandgap can be larger of the semiconductor quantum dots in reference to the bandgap of semiconductor material in large bulk materials. The bandgap can be tuned by the size of the nanoparticles. The smaller the particle, the larger the bandgap. This enables interesting bandgap engineering possibilities such as multi-junction solar cell based on the junctions with different quantum dot sizes in every junction. To use quantum dots for down conversion or multiple exciton generation, a sample of nanoparticles is embedded in a host material. How can the properties of an ensemble of nanoparticles be used for down conversion? Here we see the electronic bandgap diagram of two nanoparticles. The particles are at a very close distance from each other in order of a nanometer. In one particle, an electron is excited into the conduction band. It appears that in such nanoparticle systems, the quantized rest energy is not necessarily lost as heat to the lattice, but can be transferred as a quantized energy package to a neighboring quantum dot. Here, the second electron is excited into the conduction band of the second quantum dot. Now we have generated two electron hole pairs out of one photon. If other recombination loss mechanisms like Auger recombination and Shockley-Red Hall recombination can be suppressed, these electron hole pairs in both quantum dots can radiatively recombine. It means that they send out reddish photons. As a result, one bluish photon is converted into two reddish photons which can be absorbed by a PV material. Multiple exciton generation in an assembler of quantum dots is quite similar. Again, in one particle, an electron is excited into the conduction band. This quantized energy package is transferred to a neighboring quantum dot. Here, a second electron is excited into conduction band of the second quantum dot. If the charge carriers are separated and collected before they recombine, the result is that one photon is able to produce more than one collected electron. Here you see some experimental results on down conversion based on silicon quantum dots in a narrow spectral range from a paper of Wurzburg et al. The horizontal axis represents the photon emission wavelength. At around 799 meters, down conversion efficiency of 60% is achieved. Here we see the results out of a paper of Simonin demonstrating that EQ of above 100% can be achieved. The absorber layer contains lead selenide quantum dots, and in the blue region from 3.1 up to 3.4 electron volt. The quantum dots realize an EQ above 100% is achieved. The challenge is to move this spectral response to lower photon energies as the solar spectrum contains far more photons in this spectral range. Spectral upconversion is the process in which two or more low-energetic photons excite electrons many steps from the ground state up to the higher excited states. If the electrons occupy the higher excited states, they can fall directly back to the ground state by sending out higher energetic photons. As a result, many low-energetic photons resolve in one high-energetic photon. This photon can be absorbed in the PV active material. So, many low-energetic photons can excite charged carriers as well. Studies have been performed on materials containing rare earth ions like appium. They can pump up electrons by infrared photons to an excited level which emits in the visible light. However, the problem is that these systems have low efficiencies and only have a response in a very narrow spectral range. Next, we look at the intermediate band solar cell. This concept tries to tackle the problem that each charge carrier only has a single population state. Here we see a semiconductor material with valence and conduction band. An intermediate band material contains a narrow electronic band in the band gap as well. Such structure is believed to increase the spectral utilization. The high energetic photons can excite an electron from the valence band into the conduction band just like a normal semiconductor material. The difference is that photons below the band gap can excite an electron from the valence band into the intermediate band. The second photon is required to excite the electron from the intermediate band into the conduction band. Various ideas exist how these charge carriers are excited, transported, and collected in those devices. Most important is that the photons below the band gap also result in an excited charge carrier. In addition, the two photons with energy smaller than the band gap can effectively result in quasi-Fermi level splittings, larger than the energy of one of the low energetic photons. The last concept we will discuss is the hot carrier solar cell. It basically improves the bandgap energy utilization. Here we see the light excited charge carriers in the semiconductor material. The population of the charge carrier level reflects the situation just after the excitation by the absorption of a photon. This distribution is not in thermal equilibrium. The electrons are excited into a position higher in the conduction band. The holes are excited down to a lower level in the valence band. Such charge carriers are called hot electrons and hot holes. It takes only a few picoseconds for the hot charge carriers to relax back to the edges of the electronic bands. A hot carrier solar cell is based on the collection of charge carriers when they are still hot. It means that the energy larger than the bandgap energy could be utilized per excited charge carrier. The fundamental challenge is to collect the hot carriers before they relax back to the edge of the electronic bands. Such a concept would require selective contacts. These are contacts which only select electrons above a particular energy level in the conduction band, and contacts that selectively collect holes below a certain energy level in the valence band. In theory, the bandgap utilization could be higher than the bandgap itself. At the moment, the main challenge is to increase the lifetime of the hot charge carriers such that they have the time to move from the absorber layer to the selective contacts. Therefore, currently the main focus is on the third generation solar cells that can deliver economic, highly efficient cells that can emerge as a new technology in the near future as shown here. The second figure shows the relation between the solar cell production cost per square meter with the solar cell module efficiency and the cost per unit power.